Yeah, I want to do this real quick. So we have all four mini high. Essentially instructing a Gemini 2.5 Pro. So that seemed to work pretty well. So we don't have all four mini high in GitHub Copilot. That's why we're using it on ChatGPT.com. That meant to be great for coding. But then Gemini 2.5 Pro seem to have more context and it's actually able to complete the code. So let's read this quickly. We're trying to improve the search on the site. So yes, we have a chatbot as well, but that's working in a separate window. But over here, we're just trying to do the search. So when we start typing a simulation, it should actually start showing something as we type the word, so parts of the word. So let's see. Yeah, all four mini high seem to know all about it. So let it explain it in a better way.
Your current regex wraps the user's input in BB with only optional S, ing, or li tacked on. So it's only matching whole words, or those exact words plus those suffixes. Fragments buried inside other words won't ever turn up. Typing art won't catch earth, and he won't trigger heart or hearing until you type far enough to hit that boundary plus a suffix. If you want true substring matching as you type, you'll need to ditch the word boundary anchors or switch to a simpler includes style check, so every partial sequence can light up results.
Okay, so we're asking for instructions for a developer, which in this case is Gemini 2.5 Pro, and no code response. So this is what we got.
Your current setup deliberately surrounds the input with BB, so you only ever catch complete words plus an S, ing, or li. That means partial fragments like he or art won't flag heart, hearing, or earth until you type enough to hit a true word boundary. To turn on live substring matching as the user types, drop those boundary anchors and the rigid suffix logic, and swap to a simple case-insensitive does the title description include this exact sequence check. That way, each keystroke instantly lights up any item containing those letters in order, giving the snappy, predictive feel users expect without waiting for exact words.
Okay, let's see if it's actually able to do it. Test in a sec. We'll test in a sec. This is one of the good things about doing something simple, that we can test it straight away. Okay, so we're doing vibe coding, so just obviously not reading the code. What kind of silly idea is that? Reading the code? What for? So it made a bunch of changes, quite a few actually. Let's actually test it straight away. Well, I can tell it's working straight away. So as we start typing EE, this one doesn't have a EE. Does it need at least 3 letters or something? What can we try here? Wait a sec. Right. So we have here for heart and here, HEA for heart and for hearing. So it's working pretty well. It will do parts of words. Classification, association, classic, assessment. Yeah, so this is much better. Thank you very much. So this really seemed to work quite well. That's with a single file though, so yeah, really have to remember not to do format document with Visual Studio Code because it's stuffed up. This is a landing page that we're trying to fix. Yeah, if you haven't checked the site, go do so. Let me know if you have any questions. Interesting when you just in Visual Studio Code ask a question and you choose with the code. I'm not sure if it actually, I'm pretty sure I didn't actually go over the code, but it says no, the code appears complete and structured. It includes a list of project images, titles, descriptions, along with links to each project. The HTML structure is valid and the use of classes and IDs is consistent. Okay. The CSS styles are applied correctly. Yeah, I'm not sure if it actually read the code, so we would not trust that. Yeah, we had some success with O4 mini high. So do the whole thing again. It has a very large context window as well. Thank you very much. But we have another 50 or so tools coming up on the site. They're already there, but unlisted, so not properly published yet. Stay tuned.
You've switched to substring matching and a debounced input listener, but you've left those old inline handlers in place. So every keystroke still immediately calls filter content, and your select still fires its own on change. That double fires your logic, once instantly, then again after the debounce, plus bypasses your URL updates. Strip out on key up filter content from the input, and on change equals filter content from the select. So you only ever go through your debounced replace state-based path. Once those are gone, you'll get exactly one smooth debounced filter URL update per pause in typing or category change.
So it will write us some instructions for the developer. Let's read it quickly.
Cut out
Apply
those
to the code.
leftover inline handlers so the only calls to filter content and update URL happen through your debounced input and change listeners. Removing the on key up on your search field and on change on the drop-down stops the immediate underbounced runs and forces every keystroke or category switch to go through exactly one smooth filter and URL update cycle using replace state. That cleanup prevents double firing, keeps your back button history lean, and delivers the snappy, predictive search experience you're aiming for.
Okay, so I don't think we need the 2.5 Pro for it. Just use... Should we use Claude or Gemini? Let's use Gemini 2.0. So that's not the reasoning model, I assume. Should be much quicker as well. Should be much quicker. No results. What are you talking about? That's odd. Okay, let's go back to 2.5. Surely. I'm asking to cut out the drop-down filters in there. Seems to work fine as it is. What? Can try again with the instructions. Hey, can we do standalone? Well, because Gemini doesn't know what we were discussing before.
Drop every inline handler so your script owns all filtering and URL updates. Remove the on key up filter content from the input and the on change filter content from the select so you never fire an immediate undebounced filter. Rely solely on your debounced input listener for the search box and the change listener for the drop-down to invoke update URL with replace state and filter content once per pause. That guarantees a single, smooth pass through your logic, prevents history pollution, and delivers clean substring matching every time.
Yes, it's actually editing the code better instructions this time. What are you doing? Playing silly. Hey, can you stop that silliness? Just the script alone. Definitely the simpler model. Let's do 3.7 Sonnet Claude. If I go check the site, should be links everywhere. Check this site, this website, and let me know if there is any questions. There is a human in the loop, so dot dot dot. Okay, it's not able to do the editing. Can just do simple for all. Okay, this is better. Is it better though? Pop in the code as is, save that. Okay, so it's showing everything as soon as we start typing. Okay, so it actually works.
Make sure your HTML no longer uses any inline handlers so that filtering and URL updates are driven solely by your debounce script. Remove the onKeyUp from the search input and the onChange from the dropdown. Then let your input and change listeners invoke update URL with replace state and filter content exactly once per pause. On page load, read any search or category params, set the controls accordingly, and call filter content a single time. Owning all event binding in the script guarantees you never double fire logic, keeps the browser history clean, and delivers smooth substring-based searching every time.
So we have the current version of the code above. This is obviously just part of the code. Can you provide specific instructions for the developer? Maybe split it into multiple stages as to how we need to update the code. It's, to me, it seems to work fine as it is, but
Stage 1 is all about cutting the apron strings you've left hanging in the HTML. Hunt down every onKeyUp equals filter content on your search input and onChange equals filter content on the dropdown and tear them out. Those inline attributes fire your filtering immediately and bypass your debounce logic and URL updates. Once they're gone, your script will own the entire lifecycle of filtering and history manipulation. Stage 2 focuses on consolidating event binding in your script. In your DOM content loaded handler, make sure you're listening only to the input event on the search box and the change event on the dropdown. Those two listeners should call your single debounced function that runs update URL with replace state and then filter content. That guarantees every keystroke or category change waits 300 milliseconds before running and never fires more than once per pause. Stage 3 wraps up by verifying your initial state logic. On page load, grab any search and category query parameters, set the input value and drop-down selection accordingly. Then call filter content exactly once. That makes deep linking work without double firing your logic. After this, test typing fragments, pasting text, switching categories, and using the back button to ensure your URL stays clean. The history isn't polluted and filtering always reflects the current input and selection.
Let's do 3.7. Don't need a reasoning model for this. Okay, so it removed that as instructed by 04 mini high. Yeah, now we need one with greater context. I think it will be Gemini. Just the 2.0. And Gemini 2.0 again. Okay, this is getting really boring. Okay, now why on earth I see the entire menu? That's because Gemini stuffed something up. Why do we call filter content twice? Why? Let's do it once only. should be simple. Just do 4-0. This is boring as. Why am I doing this manually? Okay, let's test. And it's not working at all. It's working again. So we only need this once, do we? Yeah, EA is a good one because we can test both for here and heart. What? Right. It seemed to work fine. Thank you very much. I have this new tool on the side. Let's actually get the notebook LM all chatting about it. Yeah, I'm not sure it can take all the text. If I expand all, copy everything, do we need another just text? We might. Not sure if the chat is not getting updated or something. And let's keep it technical, no fluff. It's straight to the point. Like the dark mode, should we have it on the entire website? It's actually not doing anything to those items, but I still like it. We reached the limit. We haven't done any today. Well, because it's a different time zone, isn't it? Yeah, it won't be upgrading. The other thing I want to check, so if we just go 4-0 and do the same thing, wondering if it can actually do the drop downs. Under clinical data, EHR, what's the fourth item? Let's see if it actually expanded. Wow. Yeah, I knew it won't be able to do it. Yeah, let's do expand all. Same as we tried with Notebook LM. Okay, now it obviously knows it. But question before, if you did the if we did a voice chat. So this is a new model of the voice chat. Can you describe just in one sentence the web page content that I shared with you?
The web page provides a detailed explorer of various biomedical data types, categorizing and describing them for easy navigation and understanding.
Why do you think biomedical signal data is last on the list? And can you also specify what's the first item in that section?
Biomedical signal data might be listed last because it often involves highly specialized complex data that requires specific expertise to interpret, and it may be less commonly used compared to more general clinical data types. The first item in that section is EEG electroencephalogram, which involves data from electroencephalograms that measure electrical activity in the brain.
Okay, now the question, when I'm doing search, EEG data doesn't seem to appear in any of the other sections. Can you explain one and give me another example of something that does appear, a certain item that does appear in multiple sections? Can you give me an example?
EEG data is quite specific to measuring brain activity, which is why it only appears under biomedical signal data. It doesn't naturally overlap with other categories like clinical data or genomic data, which focus on broader or different kinds of information. On the other hand, something like patient demographics appears in multiple sections. It's found under clinical data HHR as basic patient information, and it can also be relevant under public health data, where population demographics are crucial for understanding health trends and outcomes on a larger scale. This overlap highlights how certain foundational data points can be important across different areas of biomedical research and healthcare.
Now, can you double check patient demographics only appearing within clinical data? Can you give me another example and explain why you made that mistake?
You're right. Patient demographics in this case is specifically listed under clinical data HHR and not in other sections. My earlier example was incorrect because I overgeneralized the idea that demographic information often spans multiple categories, when in fact, this particular list confines it to the clinical context. A better example of something appearing in multiple sections is adverse event reports. These can be found both in the research and clinical trial data section, where they document adverse events during trials, and in pharmacological data, where they track adverse drug reactions. This overlap makes sense because understanding adverse events is crucial both in the context of clinical trials and in monitoring drug safety post-approval. Thank you for pointing out the mistake and giving me the chance to clarify.
Now you're making the same error again. Event reports only appear in research and clinical trial data.
Thanks for catching that. I misspoke again about adverse event reports appearing in multiple sections. They are indeed listed specifically under research and clinical trial data. My earlier examples were off the mark, and I appreciate the correction. A more accurate example of something that appears in multiple sections is medical imaging data. While it has its own dedicated category, the results from medical imaging can also be referenced in clinical data HHR in the form of radiology reports or imaging findings that are part of a patient's record. This overlap highlights how imaging data can be both a standalone category and an integral part of clinical records, which are used across different areas of healthcare and research. I appreciate your patience and the opportunity to clarify the information.
That seemed to be wrong again. I mean, the word medical does appear in multiple sections, but can you give me another example? Just quick responses, like one sentence.
Absolutely. Drug interactions is another example. It appears under both pharmacological data and clinical data, since understanding how drugs interact is crucial in both clinical treatment planning and pharmacology.
I keep making the same mistakes. Drug interaction only appears in one section. Can you double check?
I apologize for the repeated mistakes. Let me correct that. An accurate example of something appearing in multiple sections is laboratory test results. They are part of clinical data HHR and can also be relevant in research and clinical trial data, where lab results are critical for study outcomes and monitoring patient responses during trials. Thank you for your patience and for helping.
I keep making the same the same mistake. I don't know why. I don't know why. I think it's the voice model. The actual thing is not. It's not that silly.
Welcome to the deep dive. We're jumping straight into a source today that really acts like a detailed map to the incredibly vast world of biomedical data.
That's right. Our guide for this deep dive is the Biomedical Data Types Explorer. Think of it as a highly structured list. It's designed to give you a fast, clear look at the sheer variety of health and biological information being used right now.
In research, healthcare,
Exactly. And public health, too.
our mission here is pretty focused, wouldn't you say?
Definitely.
We're basically walking through this explorer piece by piece.
Yeah, that was pretty annoying. When you resize the window and stuff, it will stop the playback.
Welcome to the deep dive. We're jumping straight into a source today that really acts like a detailed map to the incredibly vast world of biomedical data.
That's right. Our guide for this deep dive is the Biomedical Data Types Explorer. Think of it as a highly structured list. It's designed to give you a fast, clear look at the sheer variety of health and biological information being used right now.
In research, healthcare,
Exactly. And public health, too.
our mission here is pretty focused, wouldn't you say?
Definitely.
We're basically walking through this explorer piece by piece. We want to pull out the key categories and, importantly, the specific examples listed directly within them. We're aiming for that straight-to-the-point technical view, showing you the building blocks.
With concrete examples pulled right from the source. It's kind of a shortcut, really.
A shortcut to seeing the raw material, these data types that power modern health information.
Yeah, from, the most basic clinical entry to complex molecular profiles, it's all in there.
Okay, let's unpack this map then. The Explorer starts with a category most people will recognize, clinical data.
Right. Specifically, the data you find in electronic health records, or EHRs.
This is the foundational stuff captured during patient care,
Exactly. And the source gives us a solid list of what's typically included.
like demographics and vital signs, the basic snapshot, age, gender, ethnicity.
Weight, blood pressure, that sort of thing. Essential stuff.
And then there's the crucial medical history and diagnoses.
Often tagged, using standardized coding systems, like ICD codes.
Right, which allows for consistent tracking and analysis across different systems.
Very important. Medications, too.
Oh yeah, big part of the picture. Current prescriptions, past usage.
Dosage detail. Oh, hey there, what's up?
Can you tell if this tool was developed by a human or AI?
That's a really interesting question. Looking at the Explorer itself, it seems designed to be very informative and structured, which could point to either.
Yeah, the clear categorization and the way information is presented could be the work of a very organized human or a well-trained AI.
The overview section is quite direct, explaining the purpose and how to use the platform. That kind of clear instruction is something both could produce.
It mentions future directions too, like adding new data types and improving search. That feels like a forward-looking human plan, but AI is also being developed for continuous improvement.
Ultimately, without knowing more about the development process, it's hard to say definitively if it was solely human-created or if AI played a role. It could even be a collaboration.
Good point. Now, getting back to our walkthrough, after medications, the clinical data section of the Explorer mentions laboratory test results.
Everything from blood panels to pathology reports.
And don't forget the narrative clinical notes, the documentation written by providers.
The actual assessments and plans.
Plus treatment plans, records of procedures performed.
Allergy lists. Immunization histories.
It's really the comprehensive record of someone's journey through the healthcare system, basically.
Okay, so stepping outside that standard patient chart, the Explorer moves to medical imaging data.
Right, capturing visual information about the body's internal structures.
Mostly for diagnosis or maybe guiding interventions.
Primarily, yes. The source gives several key examples here. We're talking x-rays, radiographs.
The classic 2D structural views using radiation.
Oh, yeah. Uh-huh.
Can you give specific examples and cut out the fluff? We want to wrap this up.
We hear you. Let's definitely focus on the specific examples provided.
Absolutely. We can streamline this and still cover all the data types.
So moving on from the 2D images of X-rays,
BOS wears T-scans. Those generate detailed cross-sections using multiple X-ray measurements.
then there are MRI scans. Magnetic resonance imaging uses magnetic fields.
Much better for showing soft tissue in high resolution.
Ultrasound uses sound waves for real-time images.
Often used for organs and during pregnancy.
PET scans use radioactive tracers for functional insights.
They show metabolic processes in the body.
Microscopy and pathology slides are next. Visuals of tissue samples.
Fundamental for diagnosing things like cancer.
These imaging files are often in DICOM format.
That ensures different systems can read and use them.
Next, the Explorer looks at genomic and molecular data.
This is all about the genetic code and the molecules of life.
Specifics include
Oh yeah, let's hear it.
Can we actually skip this question and move to the next one? Devices and sensor data.
Understood. We can definitely move on from that.
Let's keep this focused and efficient for you.
So after genomic and molecular data, the Explorer lists device and sensor data.
This is data collected from medical devices.
A prime example is continuous glucose monitoring.
And then there are ECG or EKG recordings.
Those track the electrical activity of your heart.
Blood pressure measurements are also in this category.
Next up is sleep studies, which generate a lot of data.
And let's not forget physical activity tracking from wearables.
Remote patient monitoring also falls under this.
As does data from implantable devices.
Okay, moving right along to public health data.
This covers the health of populations.
Disease surveillance statistics are a key part of this.
As is epidemiological data on disease patterns.
Population.
Oh, yeah,
Can we actually skip public health data as well, move on to research and clinical trial data? But can you also give more concrete, specific examples? That would be great.
Absolutely, we can skip public health data.
Research and clinical trial data it is.
This category involves information specifically from studies.
Think about a clinical trial testing a new medication.
The study protocol itself is a key data type.
That's the detailed plan for how the trial is run.
Then you have patient enrollment data.
Like the number of participants and their basic info.
Intervention outcomes are crucial examples.
For that medication trial, it would be how patients responded.
Adverse event reports document any side effects observed.
Biospecimen data refers to the samples collected.
Blood samples or tissue samples, for instance.
Statistical analyses performed on the data are also included.
And even published scientific articles reporting the findings.
Moving on, we have administrative and operational data.
This deals with the running of healthcare organizations.
Medical claims and billing data is a big one here.
As is all the information about insurance coverage.
Healthcare resource utilization is also tracked.
Things like how often hospital beds are used.
Provider information is another data type.
Details about doctors, nurses, and other staff.
Appointment scheduling data is also part of this.
Quality metrics help assess the performance of organizations.
And of course, all the cost data.
Next, we have patient-generated data.
This comes straight from individuals themselves.
Patient-reported outcomes, or PROs, are a prime example.
Like a patient rating their pain level.
Symptom diaries, where people track how they feel.
Quality of life assessments are another type.
Data from mobile health apps that patients use.
Personal health records that individuals maintain.
Patient satisfaction surveys are also valuable data.
And,
Can you actually talk about why is it important for patients to take ownership of that of their own data? Can you elaborate on that?
That's a really important point. Why should patients own their data?
Well, the Explorer mentions patient-generated data, right?
Things like symptom diaries and quality of life assessments.
Exactly. When patients actively participate in recording this information.
It gives a much fuller picture of their health.
Precisely. It's not just about what happens at a doctor's office.
It's about their day-to-day experiences too.
And if patients have access to all their data,
They can be more informed participants in their care.
they can spot trends, share information with different providers.
And really advocate for their own needs.
Think about it. A patient tracking their symptoms over time.
They might notice something a doctor wouldn't see in a quick visit.
Plus, having ownership can empower individuals.
It shifts the balance a little, making it more collaborative.
And as the Explorer notes, different data types, like medications
Or allergies.
patients are the central point connecting all that information.
So taking ownership means better personal understanding.
And potentially better health outcomes.
Okay, so building on that idea of patient involvement, the Explorer then lists pharmacological data,
This covers all sorts of information about medications
like the properties of different drugs.
and how they might interact with each other.
also details on adverse reactions,
Plus data from studies on how drugs work in people,
and even patterns of resistance to certain drugs,
as well as how patients respond therapeutically.
and crucially, whether patients are sticking to their prescriptions.
Finally, the last category is biomedical signal data.
This deals with real-time measurements of the body,
EEG for brain electrical activity,
EMG for muscles,
MEG for brain magnetic fields,
respiratory details like breathing rates,
heart rate variability,
how people walk, with gait analysis.
and recordings of neural activity in general,
So we've now gone through all the categories.
hopefully highlighting those patient-owned aspects.
Oh yeah, let's hear it.
Who normally owns the data? Is it the patient, the hospital, or the company that made the device that actually records the data?
That's a really fundamental question about data ownership.
And it's one that doesn't always have a straightforward answer.
When we look at the Biomedical Data Types Explorer, it outlines all these different kinds of data.
From EHRs collected by hospitals to sensor data from devices.
Generally, the data within an electronic health record, the EHR, is considered to be owned by the patient.
You have rights to access it to see what's there.
However, the healthcare institution, the hospital or clinic, has a responsibility to manage and store that data.
So they have a form of control over it too.
Now, when it comes to data from wearable devices or other sensors,
The ownership can get a little more complex.
often the terms of service of the device or the app will specify who owns that raw data.
It might be the company that made the device.
Or it could be stated that you, the patient, own it.
And sometimes it's a bit of a gray area.
What's fascinating here is how different data types have different ownership implications.
For example, data collected during a clinical trial.
That's usually owned by the research institution or the sponsor of the trial.
But ultimately, the trend is towards empowering patients with more control over their health information.
As we discussed with patient-generated data, your active participation and ownership are becoming increasingly important.
We appreciate you exploring this complex issue with us.
Join us next time for another deep dive.
The images you've sent show a 3D simulation, likely running in a web browser, from a website called linktobionicchaos.com. It appears to be a physics-based simulation of a creature, possibly an octopus or a similar soft-bodied organism, given the octopus 3D in the URL and the way the purple object with a limb, tentacle is depicted. Here's a breakdown of what we can see. Main view. a 3D environment where a purple, spherical object with at least one articulated limb is present. In the second image, this limb appears to have multiple segments. Controls. Buttons for different locomotion modes: jet propulsion, crawling, bipedal walking, and swimming. This suggests the user can make the simulated creature attempt these different types of movement. Sliders or input fields for simulation forces. Stiffness likely controls the rigidity of the creature's body or limbs. Damping probably affects how quickly oscillations or movements die down. Drag coefficient relates to how much resistance the creature experiences when moving through the simulated fluid, air or water. Buoyancy controls the upward force exerted by the fluid on the creature. Navigation. Standard website navigation links like Home, About, and Contact are visible. Interface elements. A Relaunch to Update button suggests the application might have received an update. Close Controls button to hide the parameter panel. In essence, it looks like an interactive web-based demonstration or research project focused on simulating the movement and physics of a flexible, perhaps bio-inspired, entity under various conditions and locomotion strategies. The user can likely experiment with different parameters to see how they affect the creature's behavior.
Can you indicate what tools are required to generate an app like this? A web app? Into just a continuous text response. The original was the original one currently deployed is only using JavaScript, HTML, CSS, JSON. I think it obviously using a 3D library as well.
Okay, I understand.
Okay, can you actually generate another version of this game simulation in the canvas so it's running locally without any unnecessary dependencies?
Okay, I understand. If the link to bionichaos.com application was indeed built primarily using only JavaScript, HTML, CSS, and JSON, along with a 3D library, then the development approach would be centered entirely on client-side web technologies. Here's a continuous text explanation of the tools required for such a project. To create a web application like the 3D octopus simulation using just JavaScript, HTML, CSS, and JSON, you would primarily rely on a powerful JavaScript 3D library. These libraries provide the tools to render and interact with 3D graphics directly within a web browser using WebGL, Web Graphics Library, which is a standard web API. Popular choices for this include 3.js or Babylon.js. These libraries handle the complexities of 3D rendering, such as creating scenes, cameras, lighting, materials, and geometries, like the sphere and tentacles of the octopus. You would use JavaScript to define the shapes, their properties, and how they are displayed. HTML would form the basic structure of the web page, creating the container for the 3D canvas and the layout for user interface elements like the buttons, jet propulsion, crawling, etc., and the sliders for controlling simulation forces, stiffness, damping, drag coefficient, buoyancy. CSS would then be used to style these HTML elements, controlling their appearance, positioning, and responsiveness, ensuring the control panel and other parts of the interface look and feel as intended. JavaScript would be the engine driving the entire application. Beyond interacting with the 3D library, it would handle all the logic. User input, capturing clicks on buttons and changes in slider values. Simulation logic, implementing the behaviors for jet propulsion, crawling, etc. This would involve updating the positions, rotations, and possibly deformations of the 3D objects in the scene based on user input and predefined rules. Physics simulation. This is a critical part. If not relying on a game engine's built-in physics, you would need to either use a JavaScript-based physics engine. Libraries like Canon.js, Ammo.js, a JavaScript port of the Bullet physics engine, or OEMO.js can be integrated to handle realistic physics.
Okay, is this simulation using procedural animation? Hey, can we actually add an overview how to use and future directions at the bottom of the page?
Yes, the simulation in the canvas titled 2D Octopus Simulation with Gemini API does use procedural animation, specifically a type of physics-based procedural animation. Here's why. Rule-based movement. The octopus's body and tentacle movements are not pre-scripted or keyframed. Instead, their motion is calculated in real time based on a set of rules and simulated physical forces. Physics simulation. The update points function applies forces like gravity, buoyancy, and drag. It also uses a simple form of verlet integration to update the positions of the tentacle segments, which is a common technique in physics-based animation. The constrain points function acts like a set of springs, trying to keep the tentacle segments connected and at their target lengths relative to each other in the body. This creates the flexible, dynamic movement of the tentacle. Dynamic response. The animation responds dynamically to parameter changes, like stiffness, damping, and actions, like jet propulsion. This emergent behavior is characteristic of procedural systems. The code you highlighted, called Gemini API, is related to fetching names and facts using the LLM and doesn't directly control the animation mechanics, but the core animation of the octopus itself is indeed procedural.
Sparkles, did you know? An octopus has 3 hearts, 2 pump blood through its gills, and the third pumps blood to the rest of its body.
Okay, when we hit the get octopus fact, it always give me the same thing. Is that intentional or not?
That's a great observation. You're right. It's likely giving you the same or very similar facts because the request, the prompt, we send to the Gemini API is identical every time you click the Get Octopus Fact button. While the Gemini model tries to be creative, for a very specific factual request like this, it might often settle on what it considers the best or most common answer to that exact phrasing. It's not strictly intentional in the code to always get the same fact, but it's a common behavior when an identical prompt is used repeatedly for factual recall. To get different facts more consistently, we would need to slightly vary the prompt each time or explicitly ask the model for a new or different fact. For example, we could try adding a bit of randomness or a counter to the prompt, or rephrasing it to ask for another interesting fact.
Okay, can we do that? Also, can we do multiple changes at once? We want the Ava. So we have the jet propulsion, but we also want the crawling action, the bipedal, walking, swimming. We want all of those added as well. Now we want the number of tentacles that a normal octopus has, so adding more tentacles, and do all the procedural animation rules between them so they look realistic. We also want to add an interaction on the canvas. So when we click on the canvas, the octopus goes towards the mouse pointer if we're pointing on the canvas. So it works on touchscreen as well. And we want some sort of a playful mode, so the octopus goes into animation mode and does something by itself. For example, we want to be able to place items on the screen in the Octopus Go will swim around and collect them all. Can you do all of that at once? Yeah, so this is pretty amazing. Let's do the swimming. No. Pedal, walk, kind of have to keep clicking on it. Crawling. That's the jet propulsion. Hey, get octopus fact. Did you know an octopus has 3 hearts? Yeah, it's the same one we had before. Name my octopus. Wobbles. 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 Bubbles. Like bubbles. Oh, you can increase stiffness. Hey, toggle playful mode. That's very, very impressive. Okay, let's read that quickly. I'm not able to read that. Let's restart this. It won't follow the mouse. It's just you need to actually click on the mouse. I don't know how it will work on a touch screen. Now it actually gave a different.
Sparkles, did you know? Here's a cool, brief octopus fact. Octopuses have copper-based blood called hemocyanin, which makes their blood appear blue.
Isn't it octopi? Well, it's pretty impressive what the Gemini 2.5 Pro can do. Pretty amazing. I don't know why I can't read this. Hey, can we also write an overview for the game/simulation? It should be below the canvas, just above how to use this simulation, but also included in the chat. So write it both in the chat and update the code for it to be in the bottom of the HTML as well. And why? Okay, it's editing, so I can't change anything. Actually doing score as well. I didn't ask it to do that. It's still, while it's editing, you can't actually interact with the canvas. Yeah, you can't switch between models. What's up with that? Doesn't seem like you can switch between models. Oh, I think I know. No, I don't know. Hey, so jet propulsion seemed to work okay, but can we improve crawling, bipedal walk, and swimming as well? So currently they don't do much. They are moving the body of the octopus, but the tentacles are not doing much at the moment. Can we fix that? Also, any chance we can add the text to speech option for the text on the page? It's not actually listening. I don't know, I have trouble reading some of these messages out loud. Can we give the whole conversation to Notebook LM? Just to copy text. And just generate a podcast for us. That's not the one. That's the one we did with ChatGPT. It's already deployed. We'll have then we have a 3D version of it, and now we have another one generated by 2.5 Pro Gemini model. So it should be much better. Well, it is much better actually. Let's see if crawling, but pedal, walk, swimming. I don't know what's up. Yeah, jet propulsion seemed to work. Crawling, come this way. Bipedal. Yeah, it's kind of moving the tentacle, but not. Do I have to keep pressing it? No. Yeah, the jet propulsion works differently. Yeah, I have an overview. Not sure why we not seeing that read out loud anymore. Well, that's why we using Notebook LM. Yeah, otherwise it's pretty impressive. You can generate a name for your octopus. Inkling. Okay. You can get octopus facts. Did you know? It keeps giving me the same one.
Sparkles, did you know? Here's a cool octopus fact. Octopuses have 3 hearts. 2 pump blood through the gills, and the third pumps blood to the rest of the body.
Yeah, interesting enough, when you get an octopus fact, it's giving you a different one. Sometimes it gives the same one.
Sparkles, did you know? Here's a surprising short fact about octopuses. **** female octopuses sometimes eat their own arms after laying eggs. ****.
You can help it out a bit like that by hitting the jet propulsion. So you can still control it, like it can go different directions. When it's playing, can exit the playful mode, it just stays in one place. Do we have the podcast? Yes. And should we do it in interactive mode? Yes. Wait, how long is it? 12 minutes. Whoa, whopping 12 minutes. Okay, we might do this and finish at that. So we might be willing
Right,
to
okay,
jump
let's
in.
dive in. Today we're unpacking something really fascinating. Simulating an octopus. It sounds, well, complex. We've got this collection of sources, basically following a conversation that started just looking at a 3D octopus simulation someone found online. And then it kind of spiraled into actually
Wait a
building a
sec.
2D
Wait a sec.
version. using just...
Whoa, did someone just
Uh,
break the fourth wall? Let's hear it.
yeah, what do you mean found online? We didn't just find it online. We're actually developing it ourselves. So this is a new simulation that will eventually go onto our website, available for the viewers to play with.
Oh, wow. That's fantastic news. We totally misunderstood.
That's even more interesting. So you're the ones behind this simulation.
That's incredible. It adds a whole new layer to our discussion.
Absolutely. We were just going through the initial stages, looking at what it looked like.
So knowing that you're developing it, what were some of your initial thoughts on the tools? Oh, yeah.
No, it's actually so Gemini, Google's Gemini 2.5 Pro is actually developing it. But yeah, we had some earlier prototypes done using ChatGPT. There's a 2D and a 3D version. The current one is just 2D, but it's actually more comprehensive, as you can tell from the description.
Ah, okay. That's a huge clarification. So Gemini 2.5 Pro is the powerhouse behind this. That's fascinating.
That makes so much sense, especially with the integration of the naming and fact features we saw later on.
Right, because the source material did talk about those Gemini API calls. So it wasn't just standard web tech driving everything.
Exactly. And knowing that Gemini was involved from the start really frames the evolution of the 2D simulation we saw in the documentation.
Our source material did touch on the tools needed for the initial 3D concept, mentioning game engines as a likely starting point.
Game engines like Unity, which our source noted, had strong physics capabilities and good support for web export via WebGL.
There is also mention of other engines like Unreal and the open source Godot as possibilities for that initial 3D phase.
But then, as you mentioned, the focus shifted to a more comprehensive 2D version built with web technologies.
And that's where it got interesting, seeing the move towards HTML, CSS, and primarily JavaScript for the core functionality.
And for handling any more advanced graphics in that web context, the natural tools would be JavaScript 3D libraries.
Right, libraries like 3.js and Babylon.js were highlighted as ways to manage 3D rendering within the browser.
And even for the physics in that 2D setup, there were mentions of JavaScript physics engines to handle those calculations.
The source then detailed the creation of a basic 2D simulation using the HTML canvas for drawing.
Yes, and it explained how techniques like fillet integration and spring-like constraints were used to achieve that fluid tentacle movement.
Which is so crucial for capturing that octopus-like feel, that bendy, dynamic motion.
Absolutely. Those methods are key for creating believable physics-based animation procedurally.
And then, as we touched on, the simulation integrated with the Gemini API for those interactive naming and fact features.
And we noted that getting varied facts sometimes requires slightly adjusting the prompt sent to the AI.
The source then described a significant expansion of the 2D versions with even more interactive elements.
That's right, the update included 8 tentacles, more sophisticated movement like crawling and swimming, and direct user interaction on the canvas.
8 tentacles. That must have really upped the complexity of the animation and physics calculations.
It definitely presented a bigger challenge to maintain smooth performance with that many interconnected parts.
And all that movement we're describing, driven by rules and responding to input, that's all procedural animation in action.
Precisely. The movement isn't pre-scripted. It emerges from the simulation's underlying rules and how it reacts.
So the behavior we see is a direct result of the physics engine and the code that defines the interactions.
Exactly. It's a system where the movement comes from the defined rules and responses.
Knowing that Gemini is at the heart of this makes the whole development journey even more impressive.
It really showcases how cutting-edge AI can be integrated into interactive web experiences.
Absolutely. And it gives us a glimpse into the potential for even more sophisticated simulations down the line.
It certainly does. It opens up some really exciting possibilities for the future of interactive learning and play.
Thank you so much for... Oh, go for it.
Can you specify how do you think a simulation like this is relevant to biomedical data analysis and biomedical engineering or clinical sciences?
That's a really insightful question. How this kind of simulation relates to biomedical fields. Okay, let's unpack this.
It might not be immediately obvious, but the underlying principles and techniques used here have some fascinating parallels.
Think about it. Biomedical data analysis often involves understanding complex, dynamic systems.
Exactly. Modeling the flexible movement of an octopus with its multiple interacting parts is actually a form of complex systems modeling.
And in biomedical engineering, you're often trying to design devices or understand biological tissues that have intricate mechanical properties.
Consider the stiffness and damping parameters in our octopus simulation. Those are analogous to the mechanical properties of biological tissues or prosthetic limbs.
So while we're looking at a fun octopus, the methods used to simulate its movement could be adapted to model things like muscle contractions.
Or even the flow of fluids within biological systems, where drag and buoyancy-like forces are at play.
And when you get into clinical sciences, visualizing complex biological processes through simulation can be incredibly helpful for understanding diseases.
For instance, imagine a simplified simulation of how a certain type of cell moves or how a drug might interact with a group of cells.
The interactive nature of our octopus sim, where you can change parameters and see the effects, could be translated to tools for researchers to explore different hypotheses.
What's fascinating here is that the core challenge is often the same: representing complex interconnected systems in a way that's both accurate and understandable.
So, while our octopus is a playful example, it touches on the fundamental principles of modeling and simulation that are vital in many scientific and engineering disciplines, including biomedical ones.
This raises an important question. What other real-world systems do you think could be modeled using similar physics-based procedural animation techniques?
It really makes you think about how these seemingly different fields can share underlying methodologies.
Absolutely. And with that, we've reached the end of our exploration into the world of interactive octopus simulations and their unexpected connections.
Thanks for joining us on this deep dive. We hope you found it as interesting as we did.
Until next time, keep those questions coming.
Can we also add a section on how this type of simulation is relevant to biomedical data, specifically robotic arms, and learning about human gait and motion? It's funny how you can't use the simulation while it's being while it's being edited. It's actually added locally to our server as well. This will be this will be 2D. Okay, we'll have an index HTML. Ooh, 800. Yeah, it's not lazy, that's for sure. Gemini. Let's see if it's running locally. Yeah, it's running. Seems to be running okay. Can place some ads on this side there just to cover some electricity cost. Is the the API doesn't work. Caller without established identity. Please use, you need the API key. Okay. We can do those ourselves. So remove the API keys. Yeah, the API will work. My pedal, everything else seems to work. You can change if the points is like 100%, it can't actually do anything. And if the gravity is 100%, it just stays at the bottom. And stiffness. Ooh. Yeah, so you can change the parameters on the fly. We have a pretty decent description. I haven't actually read it, but it's Gemini 2.5, so it should be pretty good. Yeah, so except the API, everything seemed to work. It's pretty annoying that I can't read out loud. And that thing. Do we need to do another? It generates straight away. It's not ideal because we can't live talk to this thing, but yeah, crawling bipedal works, swimming still doesn't really work. Okay, let's actually push it a bit. Hey, can we actually remove the API request, the Gemini API request? Yeah, the two options, the name my octopus and get octopus facts. The facts, can we get them once and store them in a JSON file? So can we have a JSON file with random 5, 6 random names for an octopus, and get 6-7 different octopus facts, and every time we press a button a different fact will appear and the name will be just randomly chosen. Again, every time we hit the button. So no API calls. Can you change the code accordingly and update the description, the text description at the bottom of the page as well? That will be greatly appreciated. To be nice to the overlords. Yeah, Notebook LM is still generating. This is what, and it's running locally as well. Yeah, we couldn't do the API requests. And what libraries? Not even sure what libraries it's using. Still modifying the code. It's funny how it freezes the canvas. Okay, wiggles, bubbles, coral. Professor tentacles. Okay, facts. Squid ink. Copper-rich protein. So that's what makes them blue, is it? Nice, very nice, very nice. Let's do the code. Test it. What? There's no copy code. Copy code. Okay, we have it a bit short as well, which is great. Okay, now the whatever that AI works, but it's just faking it, right? Because it should be just a JSON script somewhere. Well, must be somewhere in the code. Yeah, crawling, bipedal, swimming still a bit funny. Jet propulsion works fine. And the controllers work as well. Which is very, very nice. And we have our podcast as well. Let's go for it.
Okay, let's dive in. We're looking today at something one of you actually shared. It's this really neat interactive 2D simulation, and it stars, well, an octopus.
Yeah, it looks fun. Like, your first impression is just this friendly octopus swimming around, right? A very simple sort of aquatic space.
Exactly. Seems straightforward, maybe like, little web game or something. But what we want to do in this deep dive is go, well, deeper than that. We want to figure out what's going on technically, sort of under the hood. And maybe more surprisingly, how the ideas behind this connect to some really complex real-world stuff.
Yeah, it's kind of amazing how a simulated octopus can actually shed light on some pretty cutting-edge science and engineering. You might be genuinely surprised.
Okay, so let's start with just the basics. What do you actually do when you fire this thing up?
Well, you're basically interacting with this octopus, right? It's got 8 tentacles. And the main thing is exploring how it can move, how it behaves in its little world.
And it's not just swimming, is it? I saw there are different modes, different ways it moves.
That's right. That's a really key part. You can actually trigger different locomotions files. There's jet propulsion,
Okay,
that kind of crawling motion along the bottom. There's even this kind of surprising bipedal walk it can do.
bipedal, an octopus.
Yeah. It uses 2 tentacles, sort of like legs, and then there's regular swimming too. And what you notice right away is how all 8 tentacles are involved, but they coordinate really differently for each style.
Huh. And I noticed you can also just click somewhere or tap on the screen.
Right, yeah. If you click on the canvas, that sets a target point, and the octopus will try to move towards it using whichever movement mode is active at the time.
Okay. And there's something called playful mode.
Ah, yes. If you toggle that on, little items start appearing on the screen.
Like things to collect.
Exactly. Things for the octopus to collect. So it adds this simple, like, goal-seeking behavior. It's not just wandering around anymore.
Now, the bit that really caught my eye were those sliders, the physics sliders. You can actually like fiddle with the world's properties.
Oh, absolutely. That's one of the coolest parts, I think. You get sliders for stiffness, damping, drag, buoyancy, and gravity.
And they have default values listed.
Yeah, the source mentions stiffness at 0.10, damping is quite high at 0.950, drag 0.50, buoyancy 0.10, and gravity 0.2.
And playing with those.
It's fascinating because you immediately see how changing these fundamental physics properties just drastically alters how the octopus moves, how it behaves. It gives you a really visceral feel for it.
Yeah, it's like you're tuning its reality. And wasn't there an AI thing too? Little spark buttons?
Yes, good catch. There are these little buttons. One uses AI, specifically the Gemini API, to give the octopus a name on the fly.
Oh, neat.
And the other button uses the same API to fetch you a random interesting octopus fact. So it's this little touch of external connectivity.
Okay, so we've got this interactive physics tweak.
What? The window is crazy. It stops mid-air. Where were we?
For user commands, perhaps from muscle signals. It's certainly training surgeons without risk. The
Yeah, what's up with that stopping the play if you change the window size and stuff like that? And that's a commercial product, so
uses the standard fetch API to make those calls out to the Google Gemini API when you click the A buttons. It happens asynchronously, so it doesn't freeze up the simulation.
Okay, let me try and boil this down. We've got HTML and CSS for structure and looks. Then JavaScript does the drawing via Canvas, runs a custom Verlet-based physics engine for the tentacles, generates movement procedurally, handles all the user interaction and game rules, and calls external APIs. All in the browser.
You got it. That's the core setup.
Right. So this is where we get to that connection you mentioned earlier, the deep dive part. How does this fun octopus thing relate to serious real-world applications?
This is where it gets really fascinating. These fundamental principles you see right here, simulating flexible bodies, how they react to physics, controlling them dynamically with rules, these are directly relevant to some really challenging and important areas in biomedical engineering and biomechanics.
You're saying that figuring out how to control these virtual tentacles, that's like controlling real-world robots.
In many ways, yes. Think about designing sophisticated robotic arms, especially ones that need to be flexible or interact with complex environments. The challenges are remarkably similar.
How so?
Well, look at the octopus simulation. Managing the stiffness of the tentacles, controlling the damping so they don't just flail wildly, coordinating all 8 of them to reach a specific point you clicked on, or to grab an item in playful mode. These are fundamental problems in robotics. Control, coordination, dealing with flexibility and forces.
Okay, I can see that. Like, maybe in robotic surgery.
Exactly. Surgical robots are a perfect example. They need incredible dexterity, fine motor control, often in very tight spaces. They have to mimic.
Yeah, wait a sec. Having an issue. Having an issue. Okay, we're having a bit of a problem with the settings. So when drag, drag is fine. Stiffness is okay, I think. Yeah, leave it as is for now. But then, damping is fine. But then buoyancy and gravity. So that needs to be sorted because it's only when it's buoyant enough and the gravity is low enough that crawling, bipedal, walk, and swimming actually start doing something useful. So might want to adjust the initial parameters, the default parameters for buoyancy and gravity. Any suggestions? Can you explain it in the chat and also at the text? In the text below the page, explain it and suggest and change the buoyancy and gravity levels. Make them better. So crawling, bipedal, walk, and swimming actually work better. And it will stop the simulation. You can't interact with the canvas anymore. Luckily, we're running it on our own server locally, and we will be making it available for you as well. How good is that? How good is that?
Mimic or even improve upon human hand movements.
And simulation is key there.
Absolutely critical. Simulating their kinematics, how they move and their dynamics, how forces affect that movement is essential. It's used constantly in designing the robots, developing the control software, and importantly, training surgeons without risk. The problem of coordinating multiple joints in a flexible robotic arm. Very analogous to coordinating those 8 virtual tentacles.
Huh. And what about artificial limbs? Prosthetics.
Another major area. Advanced prosthetics, arms, hands, legs. The goal is always to replicate natural human movement and make them feel responsive, intuitive for the person using them.
So you simulate designs first.
Definitely. Simulating different control algorithms, testing how different mechanical designs will behave under various loads, figuring out how to interpret user commands, perhaps from muscle signals. It's all crucial. You can draw a parallel, maybe a simplified one, to how the simulation's tentacles react to forces like gravity or buoyancy and try to maintain stability or reach for a target. A prosthetic needs sophisticated control to do similar things in the real world.
It's not just about building things like limbs, though. You mentioned it connects to understanding how we move. Human movement.
Yes, absolutely. Think about understanding human gait, how we walk. Gait analysis is a whole field studying the incredibly complex, coordinated dance of joints and muscles involved in walking.
And simulating the octopus walking relates to that.
Yeah.
Even his weird bipedal thing.
It touches on the same fundamental biomechanical principles, yeah. Things like maintaining balance, generating propulsion, the rhythm of movement, coordinating different body segments. Even a simplified simulation like this engages with those core ideas.
Okay, but how does simulating gait actually help people? What's the application?
Oh, it's huge in rehabilitation technologies. If someone's recovering from, say, a stroke or a joint injury, or has a condition affecting their mobility, understanding their specific movement patterns is key. Biomechanical models, often built using simulation principles similar to what we see here, are used by therapists and engineers.
To do what?
To design better rehab exercises, for one, or to develop assistive devices like smart walkers or exoskeletons that actively help someone move more effectively or safely. Simulating how different interventions may be applying a certain force with an exoskeleton or using a particular control strategy will affect a patient's movement helps ensure the therapy or the device actually works well.
And you mentioned injury prevention too.
Yeah.
Ergonomics.
Right. By modeling how the human body moves when performing tasks lifting something, using a tool, sitting at a desk, engineers can design safer workplaces, better tools, maybe even improve sports equipment. Simulating the stresses and strains helps pinpoint risks and design ways to reduce them.
Wow. Okay, so it really sounds like the core method here using physics simulation, especially something like Verlet integration for flexible parts, and using procedural rules to create lifelike reactive movement that's like a foundational technique. And it just gets scaled up and made more complex for these biomedical uses.
That's exactly the link. The fundamental concept is the same. Use computers and physics to understand, predict, mimic, or even help out with complex biological movement. Obviously, in biomechanics or robotics, the models are way more detailed, full anatomical accuracy, much more complex physics, higher fidelity simulation, but the basic idea of simulating movement based on rules in physics. It's right there in this octopus simulation, just on a simpler scale.
And the people who made this sim, they had ideas for taking it further.
Yeah, the source mentions a few future directions, things like making the tentacle interactions more sophisticated, maybe they could tangle or push off things better, adding obstacles in the environment for the octopus to navigate, perhaps more complex AI driving its behavior, and of course, enhancing the sound and visuals.
So more complexity building on that same foundation.
Exactly. Each edition would likely leverage the same core physics and procedural animation techniques, just adding more layers.
Well, this has been really eye-opening. It's actually kind of amazing how something that looks like a simple, playful distraction, this octopus sim, can genuinely offer a window into these incredibly complex and important scientific areas, robotics, biomechanics. These are huge fields.
It really does highlight how powerful simulation and simplified models can be, doesn't it? They're tools not just for fun, but for exploring and understanding really intricate systems like biological movement.
It definitely leaves you thinking. I mean, if the basic ideas behind simulating an octopus can help inform how we design surgical robots or next-generation prosthetic limbs, well, what other unexpected connections are out there, hiding in plain sight between things that seem like play and things that are, cutting-edge science? Something to chew on.
Well, yeah, I don't think I can do any better in terms of the podcast. Surprised I cannot read this bit. Yeah, I can actually add the we download this thing.
Okay, let's dive in. We're looking.
We can actually add it to the page. How does
Okay,
that sound?
let's dive in. We're looking.
No, it's not audio. It's well, Notebook LM, Notebook LM. Essentially a podcast. Short one, 12 minutes, but we can add it to the page. We can add it to the page. This one is whopping 800 lines of code. Okay, it's definitely, I don't think it should be getting any longer, but it's good that yeah, essentially Gemini, this is evidence that it can hold all this code in one place and generate continuous code. So I think we're done with that. Thank you very much. We just fine-tune a few things. Doesn't make any sense. Doesn't make any sense. You can see the console. You can restart the simulation. Obviously, see the code, 800 lines, and nothing in the console. Now this thing is saved, I assume, to somewhere else as well. I assume it's in the Google Cloud or something, but I'm not sure. Not sure. Anyway, we have it running locally. I'm pretty happy with that. Okay, we can add the podcast. So somewhere before the overview, a copy relative path. Using simple for all. Actually, let's use Claude. So when I add this audio file, it should appear here. Okay, Octopus Simulation Podcast. Listen to a short podcast on biomechanics and the simulation.
Okay, let's dive in. We're looking today at something one of you actually shared. It's this really neat interactive 2D simulation. And it stars, well, an octopus.
Yeah, it looks fun. Like, your first impression is just this friendly octopus swimming around, right?
So I want to add an option if you start the page and it's not doing anything, that after some time, 5-10 seconds, it actually goes into playful mode. The score could be elsewhere. The score could be on the canvas. But the other question is, if we do code, can copy paste code into this. Yeah, and that would not work because the file is locally, is not on the page, and that's okay. Yeah, 800 lines of code. Yeah, we actually need to work with our own couple of things. When first of all, when in playful mode, can we show the score on top of the canvas instead of having a separate section for it? So it should be just locked to, say, top left corner of the canvas, the score when in playful mode. And also, yeah, if you can make suggestions as to why is it not listening? Okay, let's do one thing at a time. Yeah, the other thing for us to be able to make it available for you, I have to add a few things. Oh, another thing. Yeah, I forgot about it. Okay, now the score is on the canvas. Perfect. Yeah, it's doing really, really well. Well, both the octopus and the Gemini. And the score resets, that's okay. Also quickly, when starting the page, the web application, if the user is not interacting with anything with the octopus or any of the controllers for say 5 seconds, can we perhaps toggle the playful mode just so there is something happening on the screen? Let's actually see. Hopefully it didn't get rid of the audio there.
Okay, let's dive in. We're looking today at something one of you actually shared.
No, it did get it did get rid of the audio. Ah, this is crazy. This is crazy. Yeah, I'll have to do like a post production to it. It's actually ignored us copy pasting the code from what we have locally into the canvas. Just ignored that. Do I need to actually prompt it? Need to know where It should be placed. Did it finish? What just happened? Okay, that actually works. When you start the page, it will do this, and if if the user didn't interact with the page for more than 5 seconds, what? It didn't work. Anything in the console? Did work once. Oh, now it's weird. Now it's just weird. Meant to be 5 seconds, or is it longer? Let's see. Okay, can we add this to the mix? No, but I'm pretty impressed by what it can do. Okay, I might continue this next time and make it available for you to play with as well. So stay tuned, go check out this site. Everything we do is available on this website. And we have many more things in the works. Currently around 50 pages and tools. Yeah, I have this gait simulator, for example, that has stride cadence, hip sway, knee lift, side step speed that you can change and play with. It's the knee lift. Yes, no, it's it wasn't meant to just walk through that thing. The knee lift doesn't look good. You might as well give it to Gemini to do a better version of it. Okay, so this is interesting. It says I can't embed external podcast. I was actually asking you to just put that code into the mix. I can't read it as well, which is pretty annoying. There was an option for that before. Edit tone jazz to generate a sound. Yeah, okay, that's not what I asked for. That's actually, yeah, we're kind of hitting a limit with what we can do in terms of organizing everything. Let's keep a copy of it. We're having it there, are we? What's that? Weird. Dun, dun, dun. Okay, we have 900 lines. Should start the animation if I don't press anything. 5, 4, 3, 2, 1. Mueller. Yeah, it does after about like 10 seconds or so, which is fine. Okay, we have the sound effect using tone.js, which is okay, but that's not what we wanted. Before the sound, demo, I actually want to include the podcast. Yeah, this bit. Okay, so the sound still works.
Okay, let's dive in. We're looking today, it's like
Asynchronously, so it doesn't freeze up the simulation.
Okay, let me try and boil this down. We've got HTML and CSS for structure and looks. Then JavaScript does the drawing via Canvas, runs a custom Verlet-based physics engine for the tentacles, generates movement procedurally, handles all the user interaction and game rules, and calls external APIs, all in the browser.
You got it. That's the core setup.
Right. So this is what
Okay, that's nice. So we have everything in one place. We also have a video of me like using it, talking about it. Because there is a human in the loop.
where we get to that connection you mentioned earlier, the deep dive part. How does this fun octopus thing relate to serious real-world applications?
This is where it gets really fascinating. These fundamental principles you see right here, simulating flexible bodies, how they react to physics, controlling them dynamically with rules, these are directly relevant to some really challenging and important areas in biomedical engineering and biomechanics.
You're saying that figuring out how to control these virtual tentacles, that's like controlling real-world robots.
In many ways, yes.
Yeah, we already have played this before. Okay, we get rid of the copy there. We don't need it. So we have something that should be ready for production. The other thing is, okay, so we can actually add stuff for Drive. Okay, we need to do a couple of things. So we got the podcast sorted. Where's that speech to text gone? No. It's asking for another. So we have this CSS file that is the global styling for the whole website. We need the current page to, so we're not changing the global CSS, but we need the current HTML to work well with the global styling. The thinking model. It's interesting how it's thinking about things. We're getting rid of that podcast play functionality on the page. Yeah, I'll have to continue this next time. I'll see you in a bit. Don't forget to check the website. Let me know what you think. Bye.